Example 8, computing energy by integrating power. Figure 5 shows the power consumption in the city of San Francisco for a day in September. P is measured in megawatts, T is measured in hours starting at midnight. We want to be able to estimate the energy used on that day. Okay, so there is the graph. Okay, so the first thing we need to identify is the fact that the power rate of change of energy. So we want to write out the power rate of change of energy. Okay, so by doing so, that means that P of T is going to equal the derivative of the energy function, E prime of T. Okay, so if we take a look at, we know that when we take a look at the month of September, okay, we know that the amount of a day is from 0 hours to 24 hours. Okay, so we know that T is going to go from 0 to 24 since we're talking about the days measured in hours. So therefore what we have is we're going to have this integral that goes from 0 to 24 of our function P of T dt. Okay, so then what does that equal? Well, that equals the integral from 0 to 24, and we know that P of T is equal to E prime of T dt. So what does that tell us? Well, that tells us that we want to find the antiderivative of E at 24 minus the antiderivative of E at 0. Okay, so what does this tell us? Well, this tells us that the total amount of energy which is used on that day and in this case on that day in September. Okay, so what are we going to do? Well, we're going to use the midpoint rule. So we're going to use the midpoint rule with 12 subintervals and we can say that delta T is going to equal 2. So let's take a look at that here. So if we're going to use the midpoint rule, we just need to figure out, okay, well, if this is the midpoint, this is going to represent 1. So we're going to look at what is the estimating number here. Okay, and then at 3, what is the estimating output here? Okay, and then at 5, what is the output? At 7, what is the output? At 9, what is the output? At 11, again using the midpoint rule, what's the output? At 13, again another midpoint there. We're estimating the outputs. Okay, so let's go ahead and write out our integral. So we know again that we're going from 0 to 24 of P of T dt, okay, which is going to be approximately the following. We want to find, okay, P of 1 plus p of 3 plus p of 5 plus all the way to p of 21 plus p of 23, since again we're using the midpoint rule, times delta t. So we know that from our graph, we know that p of 1 is approximately 440. We know that p of 3, again, we're just using an estimate, is 400. P of 5 is 420. Okay, p of 7 is 620. P of 9 is 790. P of 11 is 840. Okay, P of 13 is 850. And so on. So we have 850, we have 840, we have 810, plus 690, plus 670, plus 550. And again, where are we getting that? Well, we're getting it from the estimating outputs here. Okay? And then we're going to multiply it by delta t, which is equal to 2. So when we multiply that all out, we end up getting 15,840. So therefore, we can say that the energy used was approximately 15,840 megawatt hours. Now, how do we know what units to use for energy in example 8? Well, the integral going from 0 to 24 p of t dt is defined as the limit of sums of terms of the form p of t subscript I times delta t. Now, p of t subscript I is measured in megawatts, and delta t is measured in hours, so their product is measured in megawatt hours. The same is true of the limit. So in general, the unit of measure for the integral from a to b of the function f of x dx is the product of the unit for f of x and the unit for x.